Okay, so today we're going to talk about differentiation from first principles or by first principles. So this looks really complicated and it can be really annoying and frustrating, but it is actually really useful. So imagine if I asked you to calculate the gradient at P. This can be kind of confusing because how can you calculate, when we talk about gradients, we talk about the change in y over the change in x, but how can there's no change in y and there's no change in x here because it's just stationary. So we know that, well, the gradient, we define the gradient at this point as the gradient of the tangent. So it's going to look like that, right? Sorry, it's not very neat, or it's a bit rough, but that's what the gradient at P is. It's like if you were on a roller coaster. At this point here, as you're going up, you're kind of tilted a little bit upwards, but it's pretty flat. But if you were up here, you'd be looking at the ceiling, not the ceiling, the sky. So that's what we define the gradient at P as. It's the tangent line. Think of it as a roller coaster. I think that's the best way to imagine it. So how do we calculate that if we don't have a change in y and a change in x? Well, we know that we could approximate it. Let's say we had a point here, P2. We say, okay, well, let's take the gradient of this line here. You can see it right here. We calculate the change in y and divide that by the change in x. I should have clarified, this is the graph of y equals f of x. So we give it an x value, and it's going to put it into this little function, and that's what's going to give us the y value. So we've got the x coordinate here, and the y coordinate is given by f of x. We've got x plus h1, the y coordinate is f of x plus h1. We've got x plus h2, the y coordinate is given by f of x plus h2. So if we want to calculate the gradient of this line here, we do the change in y, which is f of x plus h2 minus f of x. And that's because imagine if this was 11 and this was 2. We know that it's gone up 11 minus 2, it's gone up 9. And similarly, to calculate the change in the x, we do x plus h2 minus x. So that's just h2. And that's because in the same way, if this was 1 and this was 5, to calculate the change, we do 5 minus 1. That's how much it's gone across. So that's the gradient of this line here. But we can do a little bit better than that. Let's say we had another point here, P1. We can see that this line is a much better approximation of the gradient at P. So we do the same thing. We can do the change in the y, which is f of x plus h1 minus f of x. And then the change in the x value is x plus h1 minus x. Like if this was 3, it would be 3 minus 1. And we see that as we're going to get closer, we're going to get a better approximation each time. And so all we're going to do is we're going to say the gradient at P, we'll say MP, equals, it's going to be the limit as h tends to 0. And all that means is we're just kind of demonstrating that we're getting closer and closer. We've got h2 here, h1 here. We're going to get closer and closer and closer. That's all the limit as h tends to 0 means. So it's the limit as h tends to 0. And so to calculate the gradient, as you know, it is just the change in y over the change in x. And if you remember what we just did, we did to calculate the change in y, we did f of x plus h2 or f of x plus h1, whatever one we were doing, minus f of x. That will tell us how far up we've gone. So we're going to write that here, f of x plus h minus f of x. Let me move that across. And on the bottom, we'll have the change in the x. And again, that was just x plus h2 or x plus h1, whatever we were using, minus x. And the x is cancelled out, and we were left with h, so it's h. And so that's how we do differentiation from first principles. We say, okay, we're going to have a smaller and smaller value of h, and we're going to calculate, as h tends to 0, the change in the y, or how far up we're still going, over that little value of h that we've changed. Okay, and that's all we've got here, is we're just saying we're getting closer and closer to P, And as we get closer and closer, we're going to calculate how far up it goes divided by how far across it goes. And as we do that, we're going to get closer and closer and closer to the real value. And the real value is the limit as it tends to 0. So for our first example, we're going to look at finding the derivative of y equals f of x, where f of x equals 8x. So to do this, we're going to want to know what f of x plus h is. So just like this function, what it does is you give it a number and it multiplies it by 8. It's the same for x plus h. We're just going to, instead of writing x, we're going to write x plus h. So it's easy to get tripped up on what f of x plus h is, but just think of, imagine this was f of z. We would have 8z, and then we replace the z with 8x plus h. Just literally, whenever you see an x in the function, replace it with x plus h, okay? And we're going to rewrite that as 8x plus 8h. Okay, now that we know what f of x plus h is, we can just plug everything into this guy right here. So the derivative of our function is the limit as h tends to 0 of f of x plus h, which we've just worked out is 8x plus 8h. So 8x plus 8h minus f of x. And we know that f of x is 8x, right? That's what the function is. All over h, okay? And we can simplify that even more. So we can do, again, the limit as h tends to 0. And we see up here that we've got an 8x here and an 8x here. And we're taking it away, so these guys are going to cancel out. Okay? So we're left with 8h over h. And again, the h's are going to cancel out here. And we're left with 8. So it's the limit as h tends to 0 of 8. And that obviously is just 8 because there's no h's. It's like if you had a sequence of 8, 8, 8, 8. The limit of this sequence is obviously, it's tending towards 8. So we've shown by first principles that the derivative of 8x is 8. Okay, so for our next example, we're going to look at y equals f of x equals 3x squared. So we're being asked to find the derivative of that function. So again, as before, we're going to have to work out what f of x plus h is. So again, every time we see an x, we're just going to write x plus h. We're going to replace it. So it's 3x plus h instead of x. And we know how to do this. We're going to expand the brackets. We're going to leave the 3 there. And I'm gonna write it all the steps out just to make it clear. So we've got x plus h times x plus h. And so expanding that bracket, we're going to get x squared plus xh plus another xh. So x squared. And we've got 2 xh's, okay? xh plus xh, the outside and the inside. And the last term is h times h, so it's h squared. And expanding this out further, we're going to get 3x squared plus 6xh plus 3h squared. So now that we have x plus h, we can work on plugging everything in over here. So the derivative is going to be the limit as h tends to 0 of f of x plus h. So we're going to write everything that we just worked out, 3x squared plus 6xh plus h squared. And then we want to take away f of x, which is just 3x squared. And all of that over h. So we're going to simplify that even more. So it's the limit as h tends to 0. The 3x squareds are going to cancel out because we've got 3x squared minus 3x squared. So we can cancel these guys. And then we can work on cancelling with the h term. So we've got a 6xh here. So we divide the 6xh by h, and we're left with 6x. And we divide the h squared by h, so we're left with h. So we've got the limit as h tends to 0 of 6x plus h. And we can see, and I think it's clear that as h gets closer and closer to 0, 6x plus h is going to get closer and closer to 6x. Okay, so we're left with 6x. So what we've done is we've shown that the derivative of 3x squared is 6x by first principles. And so all this means is that if we were to sketch a graph of y equals 3x squared, the gradient at a given x coordinate is equal to 6 times the value of the x coordinate. So let's say at x equals 1, the gradient at x equals 1 is going to be 6, m equals 6. Or the gradient at x equals 3 is going to be 18. Yeah, 18. So it just means that it's going to get steep really quickly. So that's what this means. That's what f dash x means. Okay, so for our final example, we're going to look at y equals f of x equals x squared plus 6x minus 5. So again, what we're going to do is we're going to write out what f of x plus h is. So f of x plus h, and again, whatever we see in x, we're going to replace it with x plus h. So x plus h squared plus 6 times, instead of x, we're going to have x plus h. And then there's no x here, so we're going to keep it as minus 5. Sorry, we're overstepping our territory here. So simplifying that even more, I'm going to skip a couple steps. So expanding this bracket, we would get x squared plus 2xh plus h squared, like we just did. I'm just skipping a step. So pause if you need me to slow down, and you can look at the last example. And then expanding this bracket, we're going to get plus 6x plus 6h, and then minus 5. So it doesn't look like we can simplify that anymore. So we're going to go ahead with writing our limit step. So the limit as h tends to 0 of all of this, x squared plus 2xh plus h squared plus 6x plus 6h minus 5. X squared plus 2xh plus h squared plus 6x plus 6h minus 5. So we've run out of room, so I hope you forgive me. I'm gonna go under here when we're gonna take off f of x, which was x squared plus 6x minus 5. And it's important that we keep this in the bracket because we're taking off all of this. It's not just take away x squared, because if we didn't have the bracket here, we'd have minus x squared, and these guys would stay, this would stay 6x, and this would stay minus 5. But we're taking away all of this, so we need it in a bracket. And that's important because the signs are going to switch. Okay, so we see that these guys, some of these are going to cancel. Sorry, I'm going to do it over h first. So we've got an x squared here, and we're going to take off another x squared, so we can cross the x squareds out. And we've got a 6x here, and since we have a minus 6x here, we can cross these out too. And again, we have a minus 5 here, and we're taking off another minus 5. So we're doing plus 5. So again, these guys are going to cancel. That's why it was important that we had this in the brackets. Otherwise, those guys wouldn't cancel, and you'd be looking at that like, why isn't this working? And so we have 2xh plus h squared plus 6h. So we can cancel some of the h's again. So we're going to write it down here. So it's going to be the limit as h tends to 0. So we're going to have 2x, because 2x over h is 2x. And then h squared over h is just h. And we got another 6h here. So 6h divided by h is 6. So it's the limit as h tends to 0 of this. So as h gets really close to 0, this guy is going to approach 2x plus 6. So this is a nice way of showing that when we have a function with multiple terms, we can just differentiate them term by term. So x squared, we've got 2x. We've got 6x, that becomes the 6. Sorry, that becomes the 6. And then our constant term, minus 5, we know that when we differentiate constants, they disappear. So nice little proof from first principles there.